For decades, the electric vehicle industry followed the same basic rule book: bigger batteries, faster charging, and longer driving range. Every automaker in the world was competing on the same field with the same strategy. But in 2024, something happened inside a quiet engineering lab that may have changed the game completely. The results have been visible for months, yet most mainstream automotive media barely notice them. If the early data proves accurate, it won't just reshape the EV race, it could completely redefine it. Hi, I'm Matthew, and this is Street Horsepower. To understand why this breakthrough matters, we first need to understand the world it emerged from. The story of electric vehicles did not start with Tesla, despite what many people believe. Back in 1996, General Motors released the EV1, an electric car leased to customers in California. Drivers loved it. Then, unexpectedly, GM recalled every single vehicle and destroyed them. Every one. If you've never looked into the story of the EV1 and the people who owned it, it's one of the most fascinating and unsettling chapters in automotive history. The modern EV era really began in the early 2000s, when battery technology finally started catching up with ambition. Lithium-ion batteries, originally developed for consumer electronics, turned out to be exactly what the automotive world needed. They were rechargeable, scalable, and capable of storing large amounts of energy. From there, nearly every major car manufacturer followed the same formula: pack as many lithium-ion cells as possible into a vehicle, control them with advanced software, improve range with each new generation, reduce charging times, and keep repeating the process. Tesla accelerated this movement faster than anyone expected. The Roadster, launched in 2008, proved electric cars could be exciting, fast, and desirable. Then the Model S in 2012 showed the world that range anxiety, the fear of running out of power before reaching your destination, could actually be solved with enough battery capacity. By 2020, nearly every major automaker had committed to electrification. Volkswagen, Ford, General Motors, Toyota, Mercedes-Benz, everyone joined the race. And the rules seemed firmly established: more kilowatt hours, better cooling systems, faster charging speeds, and lower battery costs. That was the entire strategy. For 2 decades, companies invested billions, not to reinvent electric vehicles, but simply to improve the same core technology step by step. The industry focused on making the existing system better, cheaper, and more efficient. Almost nobody questioned whether the system itself had limits. That turned out to be the first major mistake. The problem with incremental improvement is that eventually, progress slows down. Lithium-ion batteries, despite all their success, have limits. By the early 2020s, many within the industry quietly realized they were approaching those limits faster than the public understood. Energy density, the amount of energy stored per kilogram of battery weight, continued improving, but the rate of progress began slowing significantly. The dramatic leaps seen during the 2000s became much smaller and harder to achieve in the 2020s. The chemistry behind lithium-ion batteries simply imposes physical boundaries that software updates and manufacturing tricks cannot fully overcome. At some point, you are no longer expanding the box, you are just polishing it. Charging speed introduced another challenge. Fast charging sounds impressive in advertisements, but from a scientific perspective, it means forcing huge amounts of electricity into battery cells very quickly. That process creates heat, and heat slowly damages battery chemistry. Over time, repeated fast charging can reduce battery capacity. A car that originally offered 400 miles of range may eventually drop to 350, then 300. The battery that looked incredible in the showroom quietly loses performance year after year, often before owners fully realize what's happening. Then there's the supply chain issue. the one engineers rarely enjoy discussing publicly. Lithium-ion batteries require not only lithium, but also cobalt, nickel, manganese, and several rare earth materials. Many of these resources come from only a handful of regions around the world, creating serious economic and geopolitical concerns. The Democratic Republic of Congo supplies more than 70% of the world's cobalt, while a large share of rare earth processing takes place in China. The electric vehicle revolution, the one promoted as a way to reduce dependence on unstable fossil fuel supply chains, had quietly created dependence on another fragile supply network instead. Same issue, different resource, different country. That part rarely appeared in press releases because the bigger story was far more exciting. Consumers were enthusiastic, governments were offering incentives, and EV company valuations were skyrocketing. The momentum behind electric vehicles felt unstoppable. So why interrupt the excitement with uncomfortable conversations about cobalt mining and resource dependency? But behind the scenes, engineers understood the reality. Material scientists understood it. Even some analysts quietly acknowledged it. The foundation of the EV revolution had a growing weakness, and everyone involved hoped the problem could be solved before it became impossible to ignore. Eventually, someone found a possible solution. And, surprisingly, it came from a place the automotive industry wasn't expecting. In 2024, reports started surfacing about a new propulsion and energy conversion system being developed within Tesla and SpaceX engineering teams. The technology had been worked on privately for years, mostly outside public attention. This is where much of the mainstream reporting became misleading. Most media coverage focused on Tesla's usual improvements: updated battery chemistry, better thermal systems, and more advanced manufacturing processes at gigafactories. Those were all real improvements and important developments. But hidden inside technical documents, engineering presentations, and highly specialized live streams viewed by only a small audience was something much bigger. Not an upgrade to the existing EV system, a replacement for it. The new approach reportedly borrowed ideas from SpaceX's Raptor rocket engine program. That may sound like a sudden jump into rocket science, but this connection is exactly what many automotive journalists overlooked because few of them closely follow aerospace engineering. The Raptor engine, used in SpaceX's Starship rocket, operates using something called a full-flow staged combustion cycle. For decades, aerospace engineers viewed this design as the perfect theoretical engine system, incredibly efficient but nearly impossible to build in practice. The Soviet Union achieved a limited version in the 1960s, but for more than 50 years, nobody fully succeeded. Then SpaceX did. Not only did they build one, they built many, tested them repeatedly, learned from failures, and gradually refined the system into something functional and reliable. What Tesla and SpaceX engineers reportedly adapted for automotive use was not the rocket engine itself, of course. Nobody is placing a Raptor engine inside a Model S. What carried over was the underlying thermodynamic philosophy, a new way of handling energy conversion with much higher efficiency than traditional systems. Applied to electric vehicles, this approach targets one of the biggest hidden weaknesses in EV performance. Electric motors are already far more efficient than gasoline engines. A typical gasoline engine converts only about 30% of fuel energy into actual movement, while the rest is lost as heat. Electric motors, under ideal conditions, can exceed 90% efficiency, but real-world driving is rarely ideal. Heavy traffic, highway speeds, steep hills, freezing temperatures, and constant acceleration all reduce efficiency. On top of that, modern energy management systems designed to handle these changing conditions add more complexity, more weight, and additional energy loss. The new architecture approaches the problem differently. Instead of converting battery power directly into motion in a single step, the system reportedly uses multiple energy conversion stages. Each stage operates within its own peak efficiency range, while excess energy from one stage is redirected and reused by the next. In simple terms, the system is designed to waste far less energy throughout the entire power delivery process, creating a far more efficient and adaptive electric drivetrain. The core thermodynamic principle behind this system is the same idea that made the Raptor engine so revolutionary: waste nothing. Every bit of energy that would normally disappear as heat inside a conventional system is captured, redirected, and reused. According to preliminary internal testing, results that engineers have reportedly discussed quietly for months without attracting major media attention, the system may deliver real-world efficiency gains of around 30% to 40% compared to today's best electric motor technology. And that number is far more significant than it first sounds. To understand why a 30% to 40% improvement could completely reshape the industry, you need to understand what efficiency actually means in this context. It does not mean cars suddenly become 30% faster. What it means is that the same amount of stored energy can produce 30% more usable work. In practical terms, a vehicle could achieve the same driving range while using a much smaller battery pack. That changes everything. Smaller batteries mean lighter vehicles. Lighter vehicles mean lower manufacturing costs, and lower battery requirements mean manufacturers would need far fewer lithium, cobalt, nickel, and manganese cells, the very materials global supply chains have been struggling to secure for years. You don't solve a supply chain problem simply by negotiating harder for resources. You solve it by needing fewer resources in the first place. But the impact goes even deeper than material shortages. Weight has always been one of the hidden challenges of electric vehicles. Battery packs are extremely heavy. A typical EV battery can weigh anywhere between 400 and 900 kilograms, roughly 800 to 2,000 pounds. That weight itself requires energy to move, which means larger batteries demand more power. More power requires more battery capacity. More battery capacity adds more weight, and the cycle repeats. Engineers often refer to this as the mass spiral, and it has limited EV design from the very beginning. Every additional kilogram added for more range also reduces some of the benefit because the vehicle becomes heavier. The returns gradually shrink as battery size increases, but a 30% to 40% efficiency improvement could fundamentally break that cycle. If the system requires fewer battery cells, the entire vehicle becomes lighter. A lighter vehicle needs less energy to operate, which allows the battery to shrink even further. That reduces weight again, improving efficiency even more. Instead of fighting against a vicious cycle, engineers suddenly gain a positive feedback loop, a virtuous cycle where each improvement strengthens the next. And in engineering, those kinds of cycles can create changes far larger than anyone initially predicts. This is where the connection to the Raptor engine becomes especially interesting. The full-flow staged combustion system used in SpaceX rockets succeeded because it pushed extremely close to the theoretical efficiency limits allowed by physics. It wasn't just a clever tweak or a manufacturing shortcut. It was a completely different approach to how energy conversion and waste recovery were handled. The gains weren't incremental. They were structural. Applying that same philosophy to electric propulsion could create a similar transformation. Instead of simply improving existing electric motor systems, it changes the underlying architecture itself. And according to some engineers, the most important detail is this: the technology may still be in its early stages. When SpaceX first tested the Raptor engine, its efficiency was already remarkable. But through continuous testing, iteration, and real-world operation, the performance improved dramatically over time. The first versions of this new motor architecture are reportedly already achieving 30% to 40% improvements over conventional systems. And engineers believe this is nowhere near the final form of the technology. That raises a much larger question, one the industry still doesn't fully know how to answer, not whether the system works. Early data suggests it does. The real question is, how far can it go? Right now, only a relatively small group of engineers truly understands where the ceiling might be. What makes the situation even more interesting is how experts have responded. The reaction from engineering and automotive communities has not been loud or sensational. It hasn't been aggressively dismissive either. Instead, the response has been unusually quiet, cautious, and, in some cases, noticeably delayed. And that kind of silence can sometimes say more than headlines ever could. When Tesla revealed previous breakthroughs, competitors reacted quickly and publicly. For example, when the company introduced its 4680 battery cells in 2020, engineers and researchers from rival automakers immediately began analyzing the technology. The structural battery pack design also received detailed, technical criticism within weeks. The industry understood those technologies, and it responded confidently. But the reaction to this new staged energy conversion motor architecture has been very different. Some of the most respected experts in electric motor engineering have remained almost completely silent. Others have offered only brief, carefully worded comments in technical publications, statements that essentially acknowledge the technology exists while avoiding any firm conclusions about it. One senior engineer from a major European automaker reportedly described the system as requiring further study before proper evaluation. That wording matters. Experts usually don't respond that way to technology they believe is obviously flawed. When specialists think something doesn't work, they tend to say so directly. But when they say they are still studying it, that often means they are dealing with something more complex than expected. There's a big difference between, I examined this and it doesn't work, and I'm still examining this and I'm not ready to comment yet. The first response dismisses an idea. The second suggests uncertainty and possibly concern. Privately, some researchers in thermodynamics and electric motor design have reportedly been more open in discussions shared within engineering circles. According to those conversations, many experts who reviewed the technical details believe the theoretical foundation appears sound. The efficiency claims, while ambitious, are considered scientifically plausible given the architecture being described. The biggest unanswered questions are not about whether the concept can function, but whether it can be manufactured at scale and remain reliable under long-term real-world conditions. That alone is significant. These are people whose careers are built around skepticism and technical scrutiny. They are trained to challenge extraordinary claims, not casually accept them. And perhaps the strongest signal is coming from competing automakers themselves. Volkswagen has not publicly dismissed the technology. Toyota's hydrogen fuel cell division, which might normally highlight any weakness in battery electric systems, has remained silent. General Motors, after investing billions into its Ultium battery platform, has offered no major response. Ford, which has struggled financially with parts of its EV strategy, has also stayed quiet. When established industries react cautiously to a possible disruption, it usually means one of two things. Either they believe the technology is unimportant, or they believe it could become extremely important. Right now, the careful language, delayed reactions, and noticeable absence of public criticism suggest the industry may not see this as something trivial. So who stands to lose the most if this technology performs the way early data suggests? At first glance, the answer seems obvious: traditional automakers. And yes, companies that invested tens of billions into lithium-ion battery platforms could face serious challenges if a fundamentally better system emerges. But surprisingly, car manufacturers may not be the most vulnerable group. Most major automakers already understood that current battery technology was unlikely to be the final solution forever. They have research divisions, experimental projects, and alternative development programs already underway. Transitioning would be difficult and expensive, but they at least have paths forward. The industries facing the greatest risk may actually be the raw material sectors behind modern batteries, especially lithium mining. During the 2010s and early 2020s, lithium production expanded aggressively because global EV demand forecasts predicted massive battery growth for decades. Huge investments were made across Australia, Chile, Argentina, and Nevada, based on the assumption that future electric vehicles would continue requiring roughly the same battery architecture, only at larger scale. But those forecasts depend on one critical assumption: that every new EV will keep needing enormous battery packs. If a new propulsion system delivers 30% to 40% greater efficiency, vehicles could require dramatically fewer battery cells to achieve the same range. That wouldn't just slow lithium demand growth. At global EV scale, it could fundamentally change the entire demand curve. Projects financed under the expectation of continuously rising lithium prices may suddenly look far less profitable if battery requirements shrink significantly. The cobalt industry faces an even bigger challenge. Cobalt has long been one of the most problematic parts of the EV supply chain. It's expensive, heavily concentrated in politically unstable regions, and often associated with serious ethical concerns surrounding mining practices. Battery manufacturers have already spent years trying to reduce cobalt usage wherever possible. But a technology capable of reducing total battery size by 30% wouldn't simply reduce dependence on cobalt. It could completely reshape the economics of the material itself. A technology that could eventually replace traditional lithium-ion systems would affect far more than just car companies. The charging industry could also face major disruption. Billions have already been invested into fast charging networks based on today's EV model. Large batteries, long charging stops, and dense charging stations along highways. But if future EVs can travel much farther using less energy, the entire economics of charging infrastructure could change. And quietly watching all of this is the oil industry. Oil companies have spent years preparing for the rise of electric vehicles. Their investments and long-term strategies show they expected a gradual transition away from gasoline. But a breakthrough that speeds up EV adoption by making cars cheaper, lighter, and more efficient could accelerate that transition far faster than expected. And large industries are not built to adapt quickly to sudden change. What makes this story even more interesting is that history has followed this pattern before. In 2016, many aerospace experts believed reusable rockets were still at least a decade away from being practical. Then SpaceX landed a rocket booster on a drone ship, proving them wrong almost overnight. In 2019, experts believed solid-state batteries were the future of EVs, still years away from becoming commercial. Meanwhile, a completely different approach may now be delivering efficiency gains nobody expected. The same thing happened with Tesla itself. In 2006, most of the automotive industry believed there was no real market for premium electric cars. Tesla proved otherwise. The bigger lesson here is not that Elon Musk is somehow magical. It's that large industries often become trapped by their own assumptions. Experts spend decades building careers around existing technologies, so naturally they tend to believe those technologies will remain important. Real disruption often comes from people working outside those systems. That's why this new motor architecture is so unusual. It didn't come from traditional battery research. It came from rocket engineering, from a culture focused on first principles thinking and pushing beyond what industries consider practical. Instead of asking what had been done before, SpaceX engineers focused on what physics actually allows. And sometimes, asking different questions leads to answers nobody else was looking for. What happens next depends on how this technology performs outside the lab. The cautious scenario is that the system works well in prototypes but becomes harder to manufacture at large scale. The 30 to 40% efficiency gains may shrink once mass production, supply chains, and real-world conditions come into play. But even in that case, the impact would still be huge. More efficient motors mean smaller batteries, lower costs, lighter vehicles, and better overall performance. Markets where EVs were previously too expensive could suddenly become practical. Even the conservative outcome would still reshape the industry, just more slowly. The bigger possibility is more disruptive. If manufacturing challenges are solved and the technology improves through real-world testing, just like SpaceX improved the Raptor engine over time, then vehicles using this system could reach consumers within a few years. And that would create a serious problem for traditional automakers. Rebuilding automotive supply chains takes years, not months. Most companies would need at least 5 to 8 years to fully adapt. If one company gains a major efficiency advantage now, competitors may struggle to catch up. For everyday people, though, the meaning is simple. Electric vehicles could finally become affordable, practical, and efficient for a much larger part of the world. Not because of subsidies or marketing promises, but because the technology itself genuinely improved. And that's a different kind of change. The bigger issue is that the public story around EVs has always been incomplete. Most people were told battery technology would continue improving steadily under the same system and the same industry rules. But the real picture included major problems: fragile supply chains, expensive materials like cobalt, battery weight, and the physical limits of lithium-ion technology. And now, the biggest breakthrough may have come not from traditional automakers, but from rocket engineers willing to question assumptions everyone else accepted. That's why this moment matters. The EV race isn't ending because electric cars failed. It's ending because the rules may have changed completely. The companies and engineers who understand this best are still staying quiet. Mainstream coverage is mostly focused on the wrong details, but the technical papers, early results, and engineering discussions already exist. And if those results hold true, the future of electric vehicles may look very different from what the industry expected.